One of the more interesting subjects of astrobiology is panspermia. This is the idea that organic chemicals, or better yet, microbial organisms, are able to persist on asteroids and be transferred between planets. It's scientifically plausible that microbes could survive the ejection forces, and the exposure to space, and re-entry to another planet, but at every step there is the risk that the microbes will die. Each step in the panspermia process is dangerous for living organisms, even hardy little microbes, but it can be done. There is no such risk when we're talking about just biomolecules. Raw biomolecules aren't alive, so they can't die, which means it's easier for biomolecules to be passed around via panspermia. And today, I want to tell you about a recent study that identified certain biomolecules on meteors and what this means for the origin of life. Dr. Karen Smith is a researcher at Boise State University. Her and her colleagues developed a new technique for extracting and analyzing chemical traces of cyanide in various meteorites. This new, more sophisticated technique allows them to see if cyanide exists where they could not see it before, and lo and behold, in one class of meteorites, called Cno chondrite meteorites, they found traces of carbon monoxide and a number of cyanide compounds. Dr. Smith said, quote, "Cyanide, a carbon atom bound to a nitrogen atom, is thought to be crucial for the origin of life, as it is involved in the non-biological synthesis of organic compounds like amino acids and nucleobases, which are the building blocks of proteins and nucleic acids used by all known forms of life." Unquote. What she's basically saying here is that cyanide molecules are involved in prebiotic chemical reactions. They help create the biomolecules that will then go on to create living chemical systems. Their theorized role in the origin of life is big. The researchers also discovered two cyanide compounds, called Cno Carbonyl Complexes, that contain iron. Dr. Mike Callahan, also from Boise State University, said, quote, "One of the most interesting observations from our study is that these iron cyanocarbonyl complexes resemble portions of the active site of hydrogenases, which have a very distinct structure." Unquote. Hydrogenases are interesting enzymes, and it's very interesting that he points out this structural similarity. Hydrogenases catalyze the oxidation of hydrogen, and they play a critical role in hydrogen metabolism. They exist in all bacteria and all archaea, and they were thought to have evolved very, very early in the history of life, way back when Earth's atmosphere was rich in hydrogen. The active sites on the hydrogenases are the metal-containing regions of the enzyme that directly interact with other molecules, and these active sites share a remarkable structural similarity with the iron-containing cyanocarbonyl complexes found in the meteorites. So to dig into this a little deeper, these complexes have an iron atom at their core, with 6 carbon atoms attached. A single carbonyl or cyanide group is attached to each carbon atom, creating a 6-pointed structure. Part of this structure is mirrored in hydrogenase enzymes. For example, there's the, and I preemptively apologize for the lack of a better name for this thing, there's the Fe2CN5CO3- complex, and the nickel iron hydrogenase enzyme from the sulfate-reducing bacteria Desulfovibrio gigas. Both of these organic complexes have an iron atom bound to 3 carbon atoms. 2 of these 3 carbon atoms are also bound to cyanide groups, and the third is bound to a carbonyl. Dr. Karen Smith said, quote, "When you compare the structure of these iron cyanocarbonyl complexes in meteorites to these active sites in hydrogenases, it makes you wonder if there was a link between the two. It's possible that iron cyanocarbonyl complexes may have been a precursor to these active sites, and later incorporated into proteins billions of years ago. These complexes probably acted as sources of cyanide on early Earth as well." Unquote. This is an immensely fascinating study. By identifying cyanide in meteorites, they've established the presence of precursor molecules that can help synthesize more useful biomolecules that can then lead them to the emergence of life. They can be embedded in primitive enzymes, giving them the ability to generate energy and thus sustain life and complex ecologies. These cyanide complexes, which can be spread between planets by panspermia, are like seeds, or perhaps better described as accelerants, that propagate early biochemistry and enable the emergence of life.